In this video, we're going to finally derive the relationship between the current and voltage flowing through a diode. It's important to remember that the total current flowing through a diode consists of two components: a component due to the electrons flowing and a component due to the holes flowing. But as we proceed to explain how current flows through the diode, we're going to focus on the hole current, understanding that the same reasoning applies to electrons too, just in the opposite direction. As we've discussed, there exists a certain number of minority carriers, holes in the n-doped region and electrons in the p-doped region, that arise from from covalent bonds being broken due to thermal energy. That baseline is known as the thermal equilibrium value. In this diagram, we're going to call the concentration of electrons in the p-doped region n sub p0, and that thermal equilibrium of the holes in the n-doped region, we're going to call it p sub n0. Added to this thermal equilibrium of holes here are the holes which then, by nature of the concentration of holes here, diffuse across the depletion region and combine with the thermal equilibrium concentration to give us a new level of holes right at the border. It can be shown that the number of holes that diffuse here is a function of the voltage across the PN junction. And in fact, the total hole concentration here then is we're going to call P sub n at x sub n being the edge of the depletion region. The whole concentration at the edge of the depletion region then is given by that expression, and you'll notice that it is exponentially dependent upon V. Now, this additional amount right here above the thermal equilibrium we're going to call the excess concentration, and it's simply equal to this total amount minus the thermal equilibrium value, or the excess concentration is equal to P sub n0 e to the V over Vt minus P sub n0. We can factor out the P sub n0, and we have then the excess concentration, this amount right here. But as those holes continue to diffuse across the n region, they begin to recombine with free electrons, and so the actual hole concentration starts to decrease. The more holes there are, the more rapidly there's recombination, and so we actually get an exponential drop-off in the hole concentration as we move away from the junction, or as a function of x. So we have then the actual concentration, the total concentration of the holes in the n region is going to equal this P sub n0 plus what is left of this excess as it decays exponentially as it moves away. Or here's the initial value, the excess concentration, times this e to the minus x of n over L sub p. So this exponential term is the dying out portion as a function of x away from the depletion region. We can simplify that then, or we can insert this expression here, and we get then that the whole concentration as a function of x in the n region is equal to P sub n0 plus P sub n0 e to the V over Vt minus 1, which is this amount up here, then multiplied by this exponentially decaying term. Now this term L sub p is called the diffusion length of holes in the n material. It's the kind of the average, or it's related to how far the average hole diffuses before it recombines. It's something of a decay constant. It plays the same role mathematically as tau does in the equation modeling the discharging of a capacitor. So this expression is for the hole concentration. Now we can calculate the hole current density, and when I'm saying hole, I'm referring to the charge carrier hole, H-O-L-E. We can calculate the hole current density by taking this expression for the concentration and differentiating it. So taking the derivative then, multiplying it by QD sub P, we then end up with the whole current density as a function of x. We can determine what that whole current density is. In other words, it's the current density, it's the amps per square unit of measure, per square micron, if you will, is this expression here. We can evaluate that at its greatest point by evaluating this expression at x equals x sub n. So when x is replaced with x sub n, we have x sub n minus x sub n. That's e to the 0. E to the 0 then is 1. This term goes to 1, and we're left with, at the boundary, the whole current density is equal to this expression. Similarly, the electron current density is equal to this expression. And we can calculate the entire current flowing through this junction by simply taking the cross-sectional area of the junction and multiplying it by the sum of the whole current density plus the electron current density components. When we do that, then we get this expression. Now, if you think about it, the current flowing through the depletion region has got to be the current that's flowing through the entire device. An endless supply of holes and electrons supplied by the external source continues to supply the electrons as they recombine with holes diffusing across here. As these holes are recombining with the electrons, those free electrons are being bound up. For the current to continue to flow as holes continue to diffuse across here and continue then to diffuse through here, there needs to be a source of electrons to maintain that recombination. Similarly, as electrons then flow in this direction, there needs to be, and we will think of it in terms of an endless supply of holes replenishing the holes that recombine with the electrons that drifted on across the junction in this direction. But this is the internal mechanism we use to describe the flow of current within the diode. Clearly, from the perspective of the outside source, there is just a single current flowing. We have this legacy concept of a positive charge flowing. In reality, we know that it's electrons flowing in from the negative, or flowing from the negative terminal of the voltage source. And so we have this source that's supplying the electrons, that as the holes then diffuse and recombine here, we have a continuous supply of electrons. And thus, this expression that we come up with here is in fact the expression for the current flowing in this external circuit. But it is I, conventional current I. So even though we know the electrons are going this way, this current expression is the expression for current leaving the positive terminal of the voltage source and flowing into the p-doped end of the diode. To use a little more legacy type of terminology, the electrons then are flowing in through the cathode and the electrons leave the anode. Now we can clean this expression up just a little bit by recalling that in a doped semiconductor, P sub n, the minority carrier concentration, the concentration of holes in an n-doped semiconductor is approximately equal to n sub I squared over n sub d, where n sub d is the doping concentration of the donors, or the n-type doping. And similarly, n sub p is approximately equal to n sub I squared over n sub a, where n sub a is the doping concentration of the acceptors, or the p-type region. So this is true in general, but at the origin, or at the interface here, P sub n0 then will equal n sub I squared over n sub d. N sub p0 will equal n sub I squared over n sub a. And so we can replace those two terms there with n sub I squared over the corresponding doping concentration. And when we plug them in and factor out the n sub I squared term, we're left with this expression. And with that expression, we see that all of these terms here in front are constants. They're parameters of the doped semiconductor. Doping concentrations averaged, or this L sub p term, the measure of, or something related to how far the holes diffuse before recombining in the n region, and this L sub n is that measure of how far the electrons diffuse in the p region before they recombine. But the point is that we've got this rather complicated term, but it is a constant term, multiplied by this exponentially decaying term. This term applies both for positive V, meaning forward biased voltages, and negative V, meaning reverse biased voltages. Let's look first at when V is positive. When V is positive, we have this term dominating very quickly, and we see that that traditional exponential dependency of the current on the voltage across the diode. Now, when V is negative, this term very quickly goes to 0. E to the negative number is getting smaller and smaller as that number gets bigger and bigger. This term then goes to 0, and we're left with I equaling negative this expression. Now, we know from our previous conversations that the current flowing in the reverse biased diode was that saturation current I sub s. Therefore, this equation reduces down to I equaling negative this as V becomes reverse biased. Thus, this term right here, the constant multiplying the exponential term, must be this saturation current I sub s, where I sub s then is given by that formula. And finally, and this is where we've been working to get, this equation then becomes the equation relating the current flowing through the diode as a function of the voltage across the diode.